Hello, in this video I'll be showing a project in industrial engineering. This is a very fascinating field, but unfortunately many people don't quite understand what the capabilities of industrial engineering are. So for this project I have chosen a topic in logistics, which is inventory management. There is a helpful tool in inventory management, and it is Reorder Point, or ROP. And what ROP does is essentially helps prevent running out of inventory if we follow the optimal reordering point. That is, if we know where a specific level in our inventory, we have, let's say, X or Y products left, then we know that a new order must be placed if we want to help prevent the running out of inventory. The main idea is that ROP will be equal to demand during lead time plus safety stock. However, there are specific cases where this formula is just it's broken down into different ways of calculating ROP, and that depends if, for example, we have a constant demand or we have a demand that's constantly changing, or if our lead time is constant, or if we have a time where our lead time is actually changing too. So depending on those cases, then there's a specific formula that applies. So for this project, I have developed a machine learning model that helps predict the optimal reordering point. And so essentially, this will also output a decision, and that will be based on the ending inventory and the predicted optimal reordering point. And if the ending inventory falls below the predicted order point, then we know for sure that we have to place a new order. So how is this um, more beneficial than the classic ROP? Well, the main idea is that for ROP, you know that at some point you're gonna have a constant demand or lead time, or sometimes they're changing. One of them is changing, both of them are changing. But in real life, you cannot just say, okay, only the lead time is changing or the demand is changing, but one of them has to be fixed, right? So this actually happens uh, continuously. So maybe there's not a perfect way to model one situation that applies to all different cases within a season of your business. So in this case, the advantage of a machine learning model is that you can implement data set that takes into account that the ROP that, let's say, was calculated at some point in the season had maybe fixed demand or had variable lead time, and then those things were changing constantly. So during the training, then you know that the data set will encompass different scenarios for the ROP, so you're not bounded to just one specific case, right? Essentially, the data set will consist on, let's say, historical data, but in this case, I'm not using historical data. But what it will do is the model is fed this um, data set that will have all these components that you can see here, which the main things that we're very interested on would just be the numeric values. Like, let's say we know we have 3 items, so this model, it actually works for 3 items. Um, then we know that the we're dealing with percentages here too. So let's say current stock, it's 100% of capacity. It can go above or below 100%. Cannot go below 0 for this demonstration. And also know that, let's say, weekly outflow events, total outflow, schedule inflow, amount of schedule inflows, all that in this historical data is in different scenarios. So, and again, this historical data here has been made up for this demonstration. I'm just using arbitrary fixed values. Okay, so the data set that's being fed into the model, what it will have is the fields of review period ID, item ID, current stock, weekly outflow events, total outflow, schedule inflow, amount of schedule inflow, ending stock before the decision, optimal reorder point, optimized order quantity, and order decision. I'm dealing in terms of percentage here, and the model only assumes that there are only 3 items, just for proof of concept. So the percentage is of maximum capacity, and you can go above 100%, but you cannot go below 0. What the model will help predict using the data set is basically the optimal reordering point and the optimized order quantity. So the model is learning that the order decision will be based on the optimal reordering point and the ending stock before ordering decision. And that's because following the rule that we have to order more inventory if our ending stock falls below the optimal reorder point. The machine learning model I'm using is feed-forward neural network. And this is the foundation of deep learning, where the architecture of this model works, where data just flows in one direction, from the input to hidden layer to the output. So the system is made of ultrasonic sensors, MCU, a PC, and the prediction model. And I am placing three cups with three items. So the ultrasonic sensors in each cup will measure the level of that item in each cup. If our cup is full, then it will indicate 100%. Or if kind of overflowing, it will also indicate maybe we're above 100%. Um, so this data is being fed to the MCU, and then the MCU provides feedback to the computer. Then the computer is running the prediction model, and this will basically loop continuous reading of the sensors to the prediction model. First, the model begins training using the data set, and it is fairly quickly because it's only numerical data. After that, then I try to visualize the loss during the training. I develop a GUI that will interface with the predictive model. So essentially, I take readings from each sensor at each cup that indicates the level of the inventory at that moment. And if I take inventory out and then I refresh the information, then it will take into account that there has been an outflow. Once I'm done filling out with the table, I can actually upload all this data, and it will actually be passed into a second window. Essentially, it contains a table with all the data that has been obtained, and it will also have the machine learning prediction integrated into it. So I can do that for subsequent weeks. For example, that was week 1. Now, week 2, I repeat the same process. I get the values from the sensors, then maybe I may take some inventory from each cup, then I take another reading, and it will take that into account as an outflow. Then I upload it to the second window GUI, and it will tell me the prediction for that particular week as well. To take a closer look at what was happening at the GUI, essentially I was taking the sensor readings for each cup, and then I was taking inventory off, and then I was taking other readings, and it will take into account that the amount is less, and now it was labeling that as an outflow, and it was telling me by how much. So for example, all three items I can now begin to prepare if an order needs to be submitted, and in this case I go ahead and submitted the whole week report. In this case I have all the values in the first window, but now I have the prediction from the machine learning model. The prediction is deciding if new order has to be scheduled or not, and again that will be based on the comparison with the optimal reordering point that was from the model during that week. And I repeat the process again for the second week. So if this is sent to the predicting model, then again, I have all the values that have been stored in the first window, and the model is telling me if I need to order another inventory, and it's right now a no because I have enough inventory that it doesn't quite fall below the optimal reorder point.